Welcome back to multivariate calculus. In this video, we're going to be talking about Stokes' theorem. Earlier, we talked about Green's theorem, a way of relating an integral on a closed path to the integral in the surface when you're talking about a vector field integral for a two-dimensional vector field and a path in the xy plane. The idea of Stokes' theorem is going to be to extend that idea out into a path somewhere in three-dimensional space and a surface that encompasses that path in some other kind of orientation. Let me get my head out of the way and let's go back through a quick review here. Green's theorem told us that if we have a vector field f of xy with components little f of xy and little g of xy, and we had a simply connected region called R, and the boundary of that region is smooth. We're going to call that the curve that follows the region C, but using the partial derivative symbol in this context, we read as the boundary of R. Just a reminder that that notation exists. But when we have all of this, Green's theorem told us that the integral along this closed path of f dot dr was equal to the double integral over the entire region of this weird difference, partial g over partial x minus partial f over partial y dA. And we've seen things that kind of look like this in the past. And so our goal here is going to be to extend this idea out, extend the idea of a nice transition out of the plane and into three dimensions. In order to do that, we're going to generalize this thing that I have highlighted in blue, and we're going to call it, for a vector field f in three dimensions, the curl of f is defined mathematically as del cross f. Now, del is something that's a bit of a blast from the past. We've talked about it, but it's been several videos since we last did so. Remember, that is the vector that is taking partial derivatives in each component. And it's kind of weird to take an operator like del and treat it as a vector in order to do a cross product, but it works, and sometimes that's the thing that matters. So, our formula for cross product. In the first row, we're going to have the unit vectors I hat, j hat, and k hat. In the second row, we're going to have the components of the first vector. The components of del are the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. The components of big F are little f, little y, little f, little g, and little h, all of those functions of x, y, and z. But this is going to get very messy expanding it out, so suppressing the of x, y, and z will make my life a little bit better. Then just expanding out using our usual rule. And so we'll have the partial with respect to y of h minus the partial with respect to z of g in the I direction. We will have partial with respect to x of h minus partial with respect to z of f in the j direction. And we will have partial with respect to x of g minus partial with respect to y of f in the k direction. And that right there, if you look back, is the thing that showed up in Green's theorem. That is the part that was underlined in blue here. I've written it in this case using a slightly different notation for partial derivative, but it's the same idea. And I claim that this extension will just work naturally. Running out of space here. Right. So I'm just going to go ahead and write down Stokes' theorem, which says that now that I've extended my vector field f from a function of 2 variables to a function of 3 variables, well, the left-hand side doesn't look any different, but the right-hand side gets a little bit more complicated. All of a sudden, it is del cross f dot ds. It has turned into a flux integral. But that's okay. And if you stop and think about it, it actually does make sense, and we can make this work out. Let's consider a region in the xy plane. Well, if the region is in the xy plane, then vector ds is simply equal to scalar ds in the z direction, or in the k hat direction. And if we take our vector field, f of x, y, and z, and we call it little f, little g, and say 0 for our z component, so that our vector field stays in the xy plane. Or honestly, any constant will work, but 0 is just convenient. Any constant value for the z component of this vector field. Then, when I take del cross f, well, that means I'm going to set up my I, j, and k, partial with respect to x, partial with respect to y, partial with respect to z, f, g, and 0. And yeah, you can have the whole thing memorized if you would like, but I find that coming back here and writing out the matrix determinant makes it a little bit easier. But you can also just cheat and come up here and realize that, well, what's going to happen? Well, h is now 0. Partial with respect to z is now 0 because g is actually just a function of x and y. H is now 0. Partial of z of f is now 0 because f is just a function of x and y. And so we're left with just the thing we had before. Partial of g with respect to x minus partial of f with respect to y in the k-hat direction. And then if I take that del cross f and I dot it with ds, that means that I'm taking partial g partial x minus partial f partial y in the k-hat direction, and I'm dotting it with ds in the k-hat direction, and that's just going to give me partial g partial x minus partial f partial y ds. All right, so that's one important thing. Stokes's theorem reduces to Green's theorem. It's not really anything new. It's just taking what we already have and extending it outward into 3 dimensions. And with that plan in mind, that gives us some hope in how to interpret this idea of curl. And so the real thing that I want to think about here what is the curl of a vector field? To explore the idea of curl, I want to envision a circle somewhere in space in some orientation, and a vector field that is passing through the circle. Although the vector field itself is actually not what I'm interested in. What I'm interested in is the direction of the curl, del cross f. Let's take a look at del cross f. Right. In order to make this picture make a little bit more sense, I'm going to take the circle that I'm picturing in space and orient it so I'm looking at it edge on. And I'm going to have my curl, again, not the vector field itself, but the curl of the vector field oriented in some rotation. And I'm going to rotate this to get the maximum value of that, but that doesn't really matter all that much. But whenever I have a surface, I can orient the surface by setting up a normal vector. I'm going to choose to set up that normal vector roughly in the direction of the curl. So it's going to give me a positive direction, not a negative direction. And there's also a tangential direction, a direction that's along the surface itself. We'll call that T. All right, so we can think about that curl as having a normal component and a tangential component. We know from our early discussion of vectors that the component along a vector is going to involve a dot product. And yeah, you have to divide by a magnitude as well, but that's just a constant, and I don't really care. Just getting the basic idea here is going to be good enough for us. All right. But if I think about this vector field and I think about what happens as I tilt it, right? Not changing the magnitude, just changing the direction. You can also think of that as changing the direction of the surface compared to a vector field that's staying steady. But I can have the vector field mostly pointing in the normal direction, in which case the tangential direction is going to be 0. Or I can have the vector field pointing mostly into the tangential direction, in which case the normal direction is going to be 0. And that's where we're going to look next. If I take this mostly in the normal direction, then this is a large number. If I take this mostly in the tangential direction, then this is 0. So this is going to be large. And remember that n is really pointing in the direction of ds. This thing is large if the curl is in the normal direction. But by Stokes' theorem, if this integral is large, then that means that also the curl must also be large. The circulation of the vector field itself along the perimeter must be large. And the inverse is also true. If the curl is mostly in the tangential direction, then these integrals are going to be 0. And so it's this circulation integral that I want to pay attention to. Remember that circulation is asking us how much is the vector field moving along the circle? If it's moving along the circle predominantly, then that means that the curl is in the direction of the normal vector to the surface. If the vector field itself is not predominantly moving in that direction, if it's predominantly not moving in that direction, then that means that the curl of the vector field is either 0 itself or is pointed away from the surface or along the surface. All right. And that finally brings us to the right-hand rule that I've mentioned in the past, but here is the real idea behind it. The curl of a vector field literally tells us how the vector field is curling by following the right-hand rule. Point your thumb in the direction of the curl, and your fingers of your right hand will curl in the direction that the vector field wants to move. That's the real idea behind Stokes' theorem. When we talk about these theorems, I like to think about it in terms of a fluid flow. So if you think of the vector field as telling you the velocity of water in a river or something like that, then we can get a real intrinsic interpretation of what we're talking about with curl. Right? Get my head back out of the way, and let's draw a couple of vector fields. I'm going to draw vector field A here in yellow. And let's try to keep this. Come on. All right, so there's vector field A. And then in blue, I'm going to draw a vector field in a different orientation. Looking something kind of like that. And in each of these vector fields, vector field A and vector field B, I want to think about a paddle wheel. All right, so literally that cross is or the vector field is flow of water. And that cross is literally a wooden thing that's floating in the water. Well, in vector field A, the forces are kind of pulling this thing in every different direction. And if it's off center even a little bit, it's going to move in that direction. But if it's perfectly centered, then it's just going to stay put and the water is going to flow around it. Compare that to the cross over here in vector field B, where each of the legs of the thing are being pulled. And that's going to cause it to slowly turn. So it will start off in that orientation, then it will move into this orientation, and it will rotate around. And that's what the curl of a vector field is measuring. Given a vector field, given a picture, what does the object want to do? Does it want to stay in the same orientation or does it want to spin around? One last consequence. When you take the line integral of a vector field on a closed curve, then that vector field is going to be conservative. Or in other words, or in the other direction, if you have a conservative vector field, this closed curve line integral is always zero. And by Stokes' theorem, that means that del cross F must be zero. All right. I generally don't ask you for more esoteric ideas in these you try videos, but this is something I want you to try on your own. This I'll call a corollary to Stokes' theorem, tells us that a vector field is conservative if its curl is 0. Remember what it means to be conservative. If f is conservative vector field, then that means that f equals the gradient of phi for some potential function phi. And I guess I should at some point mention that this is a function of x, y, and z. And if we try to take the curl of that, the curl of del phi, we should get 0. All right, so I would like you to take a few minutes, work through the algebra, and see that that actually happens. See where you can get with that one, and I'll see you in the next video.